In 6.3, we are now going to transition from polygons being similar into triangles being similar. Triangles in geometry are used to prove pretty much everything else that there is. And so, unlike chapter 3 where we were saying that two triangles were congruent, these three theorems or postulates can prove whether two triangles are going to be similar to each other. That is how come when we abbreviate them, AA similarity, SAS similarity, SSS similarity, they have those little wave symbols there. You can use the abbreviations, but they stand for angle-angle similarity postulate, SAS, side-angle side similarity theorem, and side-side-side similarity theorem. These three theorems or postulates can prove that one triangle is similar or in proportion to another triangle. If you know only two angles of one triangle match or congruent with two angles in another triangle, they are similar. If one angle is congruent and two sides are proportional to another, then they are similar. And if all three sides are proportional to all three sides in another triangle, they are similar by the side-side-side similarity theorem. That's what this says. And once you know that two triangles are similar, you know that all their corresponding angles are congruent and their corresponding sides are proportional. That's the big idea behind the whole thing. So the first half of this section is going to be dealing with how do you know if they're similar? And these are your three reasons why. The second half will be dealing with problems, word problems, in which you can use similar triangles to solve missing things. And the best way to, not the best way, I think that one of the key ideas to any time we're dealing with math is like, how are you going to use this stuff in real life? I think that you ask that question. I get asked that question a lot as a math teacher. And the best way you can use similar triangles in real life is with indirect measurement. Meaning, if it'd be really hard to figure out how tall this palm tree is, because holding a measuring tape up there is not the easiest thing to do unless you're a really good climber. Okay? But you could use similar triangles and to measure how tall a palm tree is or how tall a tree is by measuring its shadow on the ground if you know your own shadow's length and your own height. Think about it. If I know my own height and my shadow, then isn't this angle going to be the same pretty much to the sun? I mean, the sun is so far away that the sun's rays are going to be coming at the same angle, right? That angle is going to be the same. The right angle, as long as you're standing straight up and down and the tree's going straight up and down, won't those two angles be the same? By angle, aren't they going to be similar to each other? And I can measure distances on the ground really easy. Mr. Paramo, why do I really need to know how tall a tree is going to be? Well, you never know. I mean, you might just so happen to have a tree that you need to know is if you cut it down, is it going to fit in your backyard? I have a picture just to prove that. Here you go. Let's see. Here's the picture. Doop, 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 doop. Look it. You can't see that very well, can you? See that log? Uh-huh. Will it fit in your backyard? This is my backyard. You might actually have to figure out if a tree will fit in your backyard. Because you might have really tall trees. And you don't know if the tall tree, when you cut them down, will it fit in your backyard or if you're going to have to cut it down by pieces. True story. Actually happened. Me. Another way you could do that, by the way, is you could use a mirror. If you put a mirror on the ground and you look at the mirror and you see an object really there and you measure your distance to the mirror, let's say there is no shadow, maybe it's a cloudy day, you don't have shadows, but you know the distance to the mirror and you see in the mirror the top of the thing, you could measure this distance and the distance below on the ground, and you could use these two triangles to figure out how tall something is. Kind of an interesting way to figure out how tall things are. Buildings, flagpoles, I don't know, things like that. So with that being said, let's go ahead and do some examples. I have number 16, 20, 23, and then of course a nice proof, 24. We have 4 examples that we can do together if you feel like doing these. In your book, you are welcome to do so. Number 16. Can you conclude that the triangles are similar? If so, state the postulate or theorem you used and write a similarity statement. If not, explain. All we see, these two things are parallel. If they're parallel, then that must mean that certain things are going to be the same. These are called the corresponding angles. Those corresponding angles are going to be congruent to each other because those are parallel lines. Those corresponding angles are going to be the same. And the small triangle and the big triangle have the same angle. M is the same in both. So are these two triangles similar? Sure. Yes, they are. If so, state the postulate or theorem you use. I'm using angle similarity. That's the abbreviation. If you want to write out the full thing, you can, but it's much easier just to write the abbreviation. And write a similarity statement. So I guess I'm going to start with triangle MST. Miss T is going to be similar to another triangle. MST is going to be similar to triangle MLN. It has to match. The second one always has to match the first one. First one doesn't matter which order you put it in. Second one, you're going to have to make sure it matches. Those are our 3 answers for 16. Number 20. A 2-foot vertical post casts a 16-inch shadow. At the same time, a nearby cell phone tower casts a 120-foot shadow. How tall is the cell phone tower? Okay, so let's go and do a cell phone tower. That's the best I can do for a cell phone tower. It looks something like that. You may have seen them. They now disguise them as palm trees and other things too. They try to make it blend in and make it look more natural. There's a cell phone tower and its shadow on the ground is 120 feet long. At the same time of day, there's this little tiny 2-foot post. It must be like a bell box or something. Maybe even smaller than that. It's 2 feet tall. And it casts a 16 inches shadow. I wrote a little note on number 20. Pay attention to matching units when setting up proportions. If you have feet going vertically and inches going horizontally, that is not going to be in the proper ratio as each other. Units need to match. It does not have to match between the two triangles. If I'm in feet over here, that doesn't matter. The answer is going to be in feet. But over here, I need to be in inches and inches or in feet for this to work. Is this easier to put feet into inches or the inches into feet? What do you want to do?
Inches into feet.
Okay, well, you guys decide what you want to do. I'm going to change the 2 feet into 24 inches. I think that's going to be easier for me. Because these are the same, then these will still be the same. If I want to know how tall this thing is, you could even set up a proportion with the units and I'll prove to you that it's going to be the same. I'm going to do something like x feet over 120-foot shadow is going to equal 24 inches over a 16-foot shadow. If I cross multiply 120 feet times 24 inches, and I cross multiply and I get 16 inches times x feet, eventually you'll divide by 16 inches, and the inches and inches will just go away, and you'll be left with however many feet are on that side, which is kind of nice when you keep the units involved. So I'm going to do 120 times 24 divided by 16. 120 times 24 divided by 16 comes out to 180 feet. Number 23. Got another little side note on 23. Pay attention to small triangles and big triangles when setting up proportions. So here we go. We have a small triangle, 10 over 12. Left side, bottom, equals, what's the left side and the bottom? I know the bottom is 6x, but what's the left side going to be?
20.
They're trying to trick some of you. Some of you will fall for it, and you'll only put the 10 that's there. But the full left side is a distance of 20. Keep that in mind. That's how they try to trick you. Cross multiply. Cross multiply. Divide by 60. Find the value of x. We did. Last example. Number 24. Number 24, when I looked at this one, I probably could have expanded this and made it slightly bigger, but this isn't too bad. Given PQ, segment PQ is perpendicular to QT, ST is perpendicular to TQ, PQ over ST is equal to QR over TV. Prove that VKR is isosceles. Now that's all they gave you. But I'm going to start off this proof by saying, yes, I know PQ is perpendicular to QT, ST is perpendicular to TQ, that's given, and PQ over ST is equal to QR over TV, that's given as well. If I'm trying to prove two triangles similar in step 4, I have to use one of those 3 postulates that I had before. And this one has a step 3 that says all right angles are congruent. So I must be using something with an angle being congruent to another angle. If the right angles are congruent, I got to name 2 angles that are right angles that are congruent to each other. I'm going to say it has to be angle Q is congruent to angle T. Notice I can actually use only a single letter here because this is the only angle that has Q as a vertex. I say that because some people wrote some things on their last test where they forgot where 2 lines intersect. You can't just say angle E. It doesn't work. You have to use 3 letters when 2 lines intersect at an angle. Now, we know that these two sides are proportional and one angle is congruent. Then they make a similarity statement. We have 3 shortcuts that prove similarity. Which one uses 2 sides and an angle? It should be SAS, similarity. I hope that makes sense to you. Now the whole thing that we're trying to prove number 6. I'm going to skip to 6. Triangle VKR is isosceles. That's what we're trying to prove. And we're going to use the converse of the isosceles triangle theorem. Since that's what we're trying to prove, we're trying to prove that this is a isosceles triangle, and we know that this triangle is similar to that triangle. We got to be using something that deals with their angles. The corresponding angles of similar triangles are congruent. They must be using something about this angle and this angle being the same in both of those triangles. If you look up here in this statement, angle R is congruent to angle V. The corresponding angles of similar triangles are congruent. It's not CPCTC because there's not of congruent triangles. They're similar triangles, and by definition, if they're similar, then their angles have to be the same. These angles have to be the same. If those two angles are the same, then the two sides have to be the same, and therefore it must be isosceles. That's the whole goal of number 24. So that's where we're going to end your notes.